In the next three sections of Chapter 7 in our ECE 301 workbook, we're going to concern ourselves with capacitance in series and parallel, talk a little bit about their physical characteristics, and then how they're used in practice. So at the top of page 87, we have section 5 of Chapter 7 on how capacitance in series and parallel can produce equivalence. And what's interesting is it's a little bit different than it was in the case of resistances. For example, remember that if resistances were in parallel, as I was just creating this diagram with capacitances, we would have used the reciprocal, the sum of reciprocals, or using that technique we did 2 at a time for parallel resistances. Well, in the case of capacitance, it's actually simpler. It's what we did with series of resistance. In other words, if the capacitance are aligned in the topology of the network in parallel, and we have separate currents flowing, this original current generated is flowing and split across 3 of them, it turns out the equivalent resistance is just simply the sum of them. All right, the same voltage appears across every single one of those capacitance. Okay, all right. So we'll look at this derivation of this equivalent by simply noting this, that, all right, so if the same voltage now is occurring across all 3 of those capacitances, and we'll assume PRC with the currents coming in here at the positive plate, then we know, because we already know the relationship, but in terms of how current is defined in capacitance, that the I1 must be C1 times dV/dt. The same too for I2 and I3. So the differences are basically just those 3 different capacitance constants. There's proportionality constants there, right? Well, but we would know from KCL that that incoming current I would have to be equal to the sum of the outgoing currents. Therefore, if this I has to be sum of those I3s, and this is what they all are in terms of the derivatives with respect to voltage, then we can factor out that same dV/dt term, because we know that's the same voltage at each capacitance. Therefore, it follows that the equivalent that we would have for this open terminal circuit there is simply just the sum of the equivalences, all right? So if they're in parallel, you simply sum the capacitance to get the equivalent. Now in series, a little bit different, okay? So down below here, farther down on page 87, we have them in series, all right? And so in this case, in a series argument, we know that it's the same current flowing through them, all right? So if we combine them in this way, then we'll see this familiar formula that we had in terms of parallel resistances, okay? So it's not too difficult to show this value, because again, the current is the same, all right, but the voltages are not, all right? So that's why we have V1, V2, and V3 there, all right? So a common technique to get really high voltage from low voltage sources, in other words, that you don't, your voltage source is not going to generate as much power, but if you take, say, N capacitors and align them in parallel, all right, in with the parallel with the source, and then you switch them into a series combination, all right? So you can play a game with switching devices, so that you have them in parallel to charge, and then you switch them into series to use that built-in charge, all right? And that's a very common technique used in, say, cardiac pacemakers, because their batteries cannot be, you cannot have real high voltage there because it's in the body, but you could deliver up to a 5-volt pulse to the heart, right, by switching the capacitors from a parallel to series configuration, all right, to get the desired pulse rate for the heart. So this is a very common way to generate high voltage when you only have low voltage sources, just playing this game of charge in parallel and distribute it in series, okay? So let's look at some physical, at the bottom of 87, let's look at some physical characteristics of capacitors, draw an illustration of a parallel plate capacitor, looking at some of the dimensionality issues we did with resistance. You'll remember we used cross-sectional area and diameters of wires to determine physical properties of the resistance. So we're going to do something similar now on page 88. So what we'll do is we'll draw 2 plates here, and then look at how the capacitance is defined in terms of the corresponding areas, all right? So if we take two plates and we'll just sort of draw one plate here, and just to skew it over sort of in a three-dimensional type of view here, we'll just skew the other plate off to the side. Okay. All right, and let's indicate the width here by W. That'll be our width of the plate, and then we'll illustrate the length of the plate this way, L. So length by width, and then of course we have this depth, how far they're separated, okay? Again, that's going into the paper there, all right? So by definition, what capacitance is in this physical framework is this particular value, epsilon times the area of the plate divided by the distance between them. So that's the distance between the plate. So again, the area, of course, is just length times width, or width times length, either way. And this new parameter here, epsilon, is what's called the dielectric constant of the material. So this is a material property, all right? Because capacitance does depend on what that dielectric layer is between the two plates, okay? So for example, if there's nothing between them, it's just air, that's another representation of a vacuum, then we define that as a default, because we can base everything off of it, and that's usually called epsilon 0, which is 8.85 times 10 to the minus 12 farads per meter, okay? And so we use this epsilon 0 as the relative dielectric constant. And so if we have other material properties, we just take factors of that epsilon 0, that's all, okay? So as indicated here, in other words, for a given capacitance, you probably are going to take a factor, we'll call it epsilon r, of the vacuum case, epsilon 0 times the area divided by d, okay? So in this case, the epsilon r is what we call the relative dielectric constant. It's what factor are you of air, right? So here's just a little table to give you those material properties that helps define capacitance. Obviously, if it's air, then there really isn't an epsilon r there, so it's just the original epsilon 0. So we could just say epsilon r is 1. Polyester is has 3 times the dielectric constant, and you can see how it ranges all the way up to water, right? With water is very large relative dielectric constant. So that just means this factor is going to be multiplied times this ratio, and so it's going to get larger and larger as you go down. The capacitance is going to increase with these materials, okay? So let's do example 5, just sort of get an illustration of this design, this physical design of capacitance. It says compute the capacitance of a parallel plate capacitor having rectangular plates 10 centimeters by 20 centimeters and separated by a distance of 0.1 millimeters. And again, we'll have to convert some units here because we're given at different unit values there. And then we'll consider the case where air and mica is used for the dielectric layer. So first of all, area, of course, for this capacitance is length times width. And it's best that we're going to represent everything in meters here. We'll convert everything to meters so we stay in the same unit. One reason to do that is notice very carefully that the dielectric constant is given in terms of meters. So it's a very good idea for all such problems to convert all your measurements to meters so you don't have to skew out when you multiply by that constant, right? So what we have here is we have 2 dimensions here. So let's say one of them is 10 times 10 to the minus 2 meters. That's 10 centimeters, okay? And the other dimension is 20 times 10 to the minus 2 centimeters. Again, I'm converting to meters. So that's why I have times 10 to the minus 2. And when we multiply that together, you're basically going to get 0.02 meters squared, all right? You're going to get 200, right, times 10 to the minus 2, and then you just move the decimal over and you're going to get 0.02, right? Excuse me, you're going to get 10 to the minus 4 times 200, okay? All right, so, so that would tell us the area, and then we know that the distance between the plates is 0.1 millimeters. Again, let's convert that. So that's 10 to the minus 1 power times what? 10 to the minus 3 meters. And so that gives us 10 to the minus 4 meters, right? If we look at the case of air, so if we look at the case of air, then epsilon 0, of course, is 8.85. Again, this is the dielectric constant, epsilon 0, used to define the relative case, 10 to the minus 12 farads per meter. So in terms of the, let's say the capacitance for a vacuum, we could call it C sub V. Then we know the epsilon r is just 1, or we just use the epsilon 0 value, so it's 1 times epsilon 0 a over d, and that's just going to be 8.85 times 10 to the minus 12 divided by the d value, which is 10 to the minus 4. We've converted everything to meters, so we should be good. And then we multiply by the area, which we have 0.02, okay? And so we just take our calculator out. That calculation would give us 1,770 times 10 to the minus 12 farads. And if we want to convert, we could just leave it in 10 to the minus 12. So that's about 1,770 picofarads, okay? So that's the capacitance you would get for the vacuum. Now, if you had mica, so the capacitance for mica, you would have to use the relative dielectric constant, which for mica, it's a factor of 7 times that of air. So you would add 7 times epsilon 0 a over d, okay? All right, and so all you have to do is multiply this value by 7. So we know automatically it's 7 times 1,770 times 10 to the minus 12 farads. And that just turns out to be 12,390 picofarads. Okay, much larger. So you're going to get a higher capacitance using micro, but you know, it's going to be an issue of cost. This is going to be much more expensive than it is to just not use any particular material between the plates. So there's a cost effectiveness issue there. So that's how you can, you know, design capacitors based on, you know, cost or layout in terms of how much materials you have or what kind of dielectric layer you can afford, and space that you're on the chip or on the circuit board that you're able to work with, right? So let's go on to page 89, and we'll do one more example before we get into a discussion of practical capacitors. So this problem says, suppose you want to design a 1 microfarad capacitor. Compute the length required for your plates of 2 centimeter width if the dielectric layer is polyester of 15 micrometer thickness, okay? So, all right, so in this case, we have to change, we're going to be given the capacitance, and now we want to get the physical characteristics. So the first thing is to note, all right, what capacitance are we achieving? We are achieving 1 times 10 to the minus 6 farads, okay? Large compared to the picofarad, all right? So that's the capacitance we want. We know by definition that's epsilon r times epsilon 0 times the area of the plates divided by that depth, or the distance between them, okay? All right? So in this case, we are using polyester. So we can go ahead, go back to that table, and the relative factor is 3.4. And of course, we know the default electric constant for the vacuum is 8.85. We just did this, right? 10 to the minus 12 farads per meter, okay? All right. So if we plug all these components in there, our goal is to see if we can figure out what the area has to be. So we're missing the area. We have everything else. So what we have is 10 to the minus 6 farads equals 3.4 times the dielectric constant 8.85 times 10 to the minus 12. And again, that's farads per meter. Just seeing how our units work out. That's being multiplied times some unknown area there, divided by, okay, they gave us the thickness at 15 mu, so that's going to be 1.5 times 10 to the minus 6 meters. Okay. So that is a typo there. That should be 1.5 there. I was going to say, I'll have to change that. It should be 1.5 micrometers. Okay. Right. So that implies, with some calculation here, that with the calculator getting out, the area then, if you solve this, all the units will work out in terms of the farads dividing out, and you're going to end up with meters squared. You should get 15 divided by the 3.4, writing it that way, times the 8.85, okay? All right. Because I think if you look carefully, what you've got here is this 10 to the minus 6, all right? If you look at the fact that if you subtracted exponents, you would get a 10 to the minus 6 here, but you have a 10 to the minus 6 on that side, so it's all going to divide out, right? Let's actually, now that I think about it, the 15 is fine. I just wrote this wrong. I'm sorry. I'm looking at my calculations. I really did want it 15. So let's leave this alone. It really should be 15 micrometers. Okay. I just had written in my notes 1.5. So that should be 15 there. Okay. All right. So the exponents all work out, divide out evenly. And so this will turn out to be 15 divided by 30.09. And that kind of makes sense based on about a 15 micrometer thickness. And so that tells us that that value of the length times the width has to be, according to calculator, divide that out, it's about a half, 0.4985, okay? Almost a half. And the goal was to get the length. If you know the dimensions is 2 centimeters, so therefore the length then must be 0.4985. Again, be careful with the units. 2 centimeters represented as meters should be 2 times 10 to the minus meters, okay, right? And again, this should be meters squared. So this is meters squared divided by meters gives us meters. And you would get 24.925 meters, or approximately about 24.93 meters. So that is how much material, or that in terms of the size of the plates, they're going to have to be almost about 25 in length. Okay, that's the length of material that you're going to need, okay, to construct these plates to get a 10 to the minus 6 Fahrenheit. Okay. All right. So so again, just applying the formula straight off, and just be careful. Again, I'll just write it one more time. It's best to convert all your units to meters, okay? Simply because of the constants that you're using are farads per meter, okay? So the last section related in this chapter on capacitors is just a discussion of what happens in the real world in terms of what levels of capacitance can you really maintain and what's realistic. And we'll do a slide example of illustrating it. So they're typically constructed, I'm at the bottom, well, in the middle and towards the bottom of page 89. They're constructed by alternating plates with 2 layers of dielectric and then rolled into a small area. So you could think it like a jelly roll kind of a situation. An electrical contact can be made with the plates from the ends of the roll, and the maximum voltage ratings are used to avoid breakdown of those materials. So for a given voltage, the electric field intensity becomes higher as the dielectric layer starts to thin, okay? So there's always this design trade-off between its size and the voltage rating, right? In the design of electrolytic capacitors, one of the plates is usually metallic aluminum or tantalum, And the dielectric is usually oxide layer on the surface of the metal. The other plate is usually a solution, electrolytic solution. And this design is heavily desirable for high capacitance per unit volume, but only one polarity of voltage can be applied, okay? So you would actually only have, because of that fluid, you're only gonna have it all positive, you're only gonna have a negative, okay, in terms of the plate. So a more realistic model of a capacitor is actually illustrated here with components that we've already seen and are about to see, because we haven't done inductance yet, but it's illustrated here in terms of what are known as parasitic effects, okay, that you're not truly getting the capacitance that you expected. Why? Well, you typically model it in this way with resistances, inductances, and so that the designs take into account that the circuit operates properly. The resistance RS reflects the material. There's a resistance due to the material itself, and that's reflected by R sub S. And then R sub P models the conduction through the dielectric. They're not perfect insulators. If they were perfect insulators, you wouldn't need this particular resistance. But since they're not necessarily perfect, we got to, again, have an effect on the current flow through the capacitor. And then finally, there's an inductance, which we will actually cover soon. That's indicated here by L, because you tend to get a magnetic field generated also, all right? So these are sort of effects in the real world that occur simply because you've got a design of a capacitance with these two plates, all right? So let's flip over and sort of take this into account in example 7. And example 7 is a very simple circuit of two capacitances, which initially are wired in a way that a switch is open and then at time 0 is closed. So that's what this diagram means when you have this kind of an open switch and they put an arrow and say T0. So at time 0, the arrow says close the switch, okay? Similarly, sometimes you may see it the other way around, and then, you know, it may look like the switch, you know, then is going to be opened at time 0. So it could go either way. The arrow will tell you which way it's opening, okay? So for the circuit below, what we have is we have two capacitances. We have C1 and we have C2, and they are both 1 microfarad capacitance. So that means 10 to the minus 6 farads for both of them, okay? And clearly when you close that switch, they're in parallel, all right? So what we've got though is a little bit different situation, all right, in terms of the setup. The C1, the one over here to the left, is charged to a voltage of 100 volts. So in other words, this one's been charged, just like, you know, you've previously used it, maybe you put a battery source up to it and you've charged it up, or even from an alternating current, whatever. You've had a source, a voltage source, charge it up, and it's storing 100 volts, right? The one over here on the right, the C2, we're going to assume has nothing, all right? So there's 0 volts there, right? So the interesting thing here is keep in mind capacitance, you can store energy in them and then they can dissipate it, right? Remember the change in the voltage. It's all about how the voltage changes, right? And your circuit. So there's nothing on this one. And this one has 100 volts. And what we're interested in is when the switch is closing and they're now wired up together, right? And current starts flowing, how much energy gets transferred from one to the other, okay? All right? So the goal is to compute the total energy stored by both capacitors before and after the switch closes, all right? So again, what's the energy before and after the switch closes? And then here's a particular note that when the switch closes, the total charge on the top plates of the capacitors cannot change because there's no path for the electrons to enter and leave the top part of the circuit, okay? All right, so let's look at the initial case. So the initial stored energy. For each capacitor, right? Going back to our formula, W1, in this case, will be capacitance C1 times that voltage squared divided by 2. That's just our formula for energy, one of them, one of the forms that we can use, right? And so in this case, for number 1, what will we have? I'll write it this way. 1/2 times what? 10 to the minus 6 is C1, correct? And we have 100 volts, and we square the value. That would turn out to be 5 times 10 to the minus 3. I'm going to write it that way, joules. And so I'm going to write that as 5 microjoules. Okay, I'm just playing a little bit with exponents there. 100 squared, of course, is 10 squared, and then that squared is 10 to the 4th. And then we're going to get 1/2, so if I want to represent that as 5/10, that's 5 times 10 to the minus 1. So either way, I mean, there's a lot of ways I can represent it, but I'm going to represent everything in this case in microjoules. Okay? W2 is easy, 0, right? So I don't need to plug in the formula because there's no voltage. So there's no stored energy, right? So initially, the total energy, if we call it subscripted totally, all right, is the sum of these two. So it's W1 plus W2, and of course, it's 5 millijoules. So that's what energy is available in the circuit, all right? In this case, before the switch closes. Okay. So, so one thing to note is that the charge, let's think about a little bit of what's going on here on C1. The charge stored, according to our assumption there, the charge stored on the top plate of C1, because it indicated that, when it closes, we can't change this, but initially, this one's got voltage on it, all right? So we can use our formula. Q1, we'll call it Q1, is what? C1V1. That's what charge is on a capacitance, right? That's how we started looking at capacitance. So if we multiply that out, again, 10 to the minus 6 times the voltage, which is 10 squared or 100. So we have 10 to the minus 4 coulombs, right? Which I'm going to convert, that's going to be the same as 100 times 10 to the minus 6 coulombs, or that's 100 microcoulombs, okay? So that's the charge that is stored on the positive plate, that top plate of C1 there, right? So that's important because now at the closing of the switch, the charge on the equivalent capacitance of the circuit is what? Think about it. What happens? Well, when you close it, they're in parallel, aren't they? So it follows then that the equivalent charge, we'll call it EQ, would have to be Q1 plus Q2, which is 100 microcoulombs, okay? Right? In other words, you would just be, summing the two, but again, we know there's no voltage here. So whether you take the equivalent, I mean, it doesn't really matter adding the two capacitances because you've got no voltage there. So the idea though is that, right when at the closing of the switch, you've got 100 microcoulombs over here, and you still have nothing over there, right? There's no charge. Nothing's happened, okay? So we've got to build the charge up, okay? So the goal is to figure out, all right, well, how much transfer? So as the switch closes, and again, let me just reiterate, that's what this statement meant. When it's closed, the total charge of the top of the plates cannot change, right? That just means whatever was there, it's that nothing has changed the minute this closes. So there was no charge there, and there was 100 microcoulombs there, so that's the total charge you've got, okay? All right? So as the switch closes, then we have C1 and C2 in parallel, is what I meant earlier. So the equivalent capacitance then becomes C1 plus C2. So that there is no equivalent capacitance until the switch closes, right? That's important because once that switch is open, you don't have any current, okay? No current flowing across the open switch, right? So, and of course, in this case, you'd get 2 microfarads, right? That's the equivalent capacitance because we add them when they're parallel. So what does that tell us about the voltage? So the voltage across that equivalent, right, would be what? Well, it'd be the equivalent voltage, which is QEQ divided by CEQ, okay? In other words, voltage is just charge divided by capacitance, right? So when you combine these, you know, into one capacitance and you need the voltage, then you're just going to divide out the ratio of whatever charge is represented in that equivalence as well as the capacitance, okay? And so in this case, it's just going to be 100 microcoulombs over 2 microfarads, and that will give you 50 volts, okay? Now I'm not redrawing the equivalent here because it would just be one equivalent and it would be 2 microfarads, right? And again, the only way you could know how much voltage you've got is you'd have to know how much charge there was on the plates, okay? And that's what the QEQ represents, right? So also, what's also true is that in that case, the voltage of the equivalent and all the other voltages, because they're parallel, are all 50V, right? So that means when the switch closes, you're going to get 50 volts distributed to each one of those, okay? They're in parallel, but the 50 volts will be distributed to each of them, okay? They'd have to be, if they're going to be the same, you're going to divide that by 2, okay? And so that tells you something about if you had several capacitances, you know, built up this way, then, you know, if one of them has charge on it and the others don't, you're going to divide that voltage evenly across all the rest of them. That's what this is showing you, okay? So the stored energy then, when the switch is closed, spelled that wrong. Is the following. Let's go back to our formula. But now we're looking at when you close it, we'll have that equivalent voltage squared over 2, right? And for the first one, so that's going to be 1/2 times 10 to the minus 6 times 50. So the voltage drops to 50, right? And ultimately what's going to happen is you're going to get 1.25 millijoules. Okay, I'm just saving a little computation time there, okay? So that's what you would have on the first one. But the nice thing is you then you're sharing the voltage then with the other one. So it's C2 times the equivalent voltage after the equivalence. And because you only have one circuit element there, one capacitance. So we could call it whatever we want to call it. So we're just calling it VEQ, right? So this will be 1/2 times 10 to the minus 6, also 50 squared. So they're the same. 1.25 millijoules. Right? And again, where did this come from? From the fact that you end up in parallel, you sum the capacitance, which would force the fact that since you only had 100 microcoulombs charge after closing the switch, then that's how much volts you've got. Okay, it's as simple as this ratio. That's what the ratio for voltage is for capacitance. But then adding these two up is interesting because now if you look at the total energy after the switch is closed, it'll be this sum, right? W1 plus W2, and that gives you 2.5 millijoules. Now, let's look very carefully. Before the switch was closed, there's your total energy. After the switch closes, that's what you have. So just obviously the observation is the value 2.5 millijoules is 1/2 of the original energy, or 5 millijoules, like that. So the natural question is, what happened? What happened to our law of conservation of energy? What happened here? Okay, if we started with 5 millijoules, shouldn't we be finishing with 5 millijoules? I mean, what difference should it make in terms of the switch closing? Well, this is the parasitic effects. So it's interesting that what we were just talking about, the missing energy is usually thought to be absorbed by parasitic resistances. Using a more realistic model could account for all of this energy. In other words, we could have counted for that if we had, rather than drawn these capacitances simply like this and using our relationships between charge and voltage, if we had designed this kind of a situation, then what we would know, we could have already predicted with these kinds of resistances that we're not going to maintain 5 millijoules down here in this capacitance, because there were these parasitic effects will be pulling off some of the energy that you would have hoped would have gotten there. But again, there are material properties at play. There's physics involved here, which suggests that you can't absolutely maintain the perfect electric field that you'd want. Okay, all right. But this is a nice little problem. It just illustrates what we know in terms of how to do equivalence and capacitance, how to use our formulas for total energy, and just making sure that we, logically, take into account what we know before and after a switch is closed, right? So in the next section, and what we'll be doing to finish out this very important chapter is the next sections will involve the inductance, which have to do with same idea of storing and releasing energy, but not using an electric field, using a magnetic field. And we'll see how they can be used to generate energy, and then how do they behave when you configure them in series and parallel.